So another 30,000 foot view video, this time on glycolysis. So let's go back to our overview of fuel metabolism and let's orient ourselves to where we're at. Well, we just digested a whole bunch of our fuels, or maybe we had some endogenous sources of either glucose from glycogen reserves, or we maybe tapped into our adipose tissue, okay? But if we're talking about glycolysis, it had to be glucose that we get from glycogen stores if we're going to be talking about an endogenous source. But regardless, we've got monomers that we've got in our bloodstream, and particularly if we're talking about glycolysis, we're talking about having glucose. Let's zoom in here so we can actually see a little bit more. Our whole next slide is really going to be about this little piece here, okay? That is glycolysis. That's glycolysis in the context of the totality of metabolism that we're going to learn about. So right now we're going to have one slide that we learn the highlights. So maybe it's more like a 5,000 foot view of glycolysis. I'm going to highlight that next semester. That's going to be your fundamentals piece that you'll have to know for glycolysis. That's going to be sort of the level of glycolysis that you need to know by the end of Biochem 2 for your final exam. But we'll actually have an entire learning unit just on glycolysis next semester. Okay, so let's go through some pieces of glycolysis that we want to know about. Remember, that was when we talked about our 4 stages of carbohydrate metabolism from glucose. We've got glycolysis, pyruvate dehydrogenase chemistry, the citric acid cycle, and then electron transport and oxidative phosphorylation. Those 4 steps. So we're at step 1. What we're going to do here for all of these 4 steps is we're going to talk about what the net reaction is. We're going to think about some details like how many steps is it? Where does it occur? Is it aerobic or anaerobic? And we're going to sort of have an overview of what happens during this process, and are there some key things that we sort of need to be able to think about? So let's start first with glycolysis, with what the net reaction is. Now, my stoichiometry is not going to be it's not going to be a balanced chemical equation, because right now all I really need you to know is the names of the pieces that we start with and that we end with. So the net for glycolysis is we're going to take glucose and we're going to break it down into pyruvate, ATP, and NADH. So at the end of the day, what we're doing is we're taking a glucose sponge, if you will, and we're going to be breaking it in half to generate 2 3-carbon pyruvate molecules, and we've squeezed a little bit of the water out of it to generate ATP. We're going to talk about how we generate that ATP, and then we've harvested some of those electrons as one of those reduced cofactors as NADH. Now, don't worry if you can't really see too much with this picture. You don't need to know the details of this picture. By next semester, when we have our entire learning unit on glycolysis, this picture will look like a simplification of what we will understand with it. But here's the pieces that I sort of need you to know, okay? We're going to be looking at glycolysis, and at its core, I want you to understand 2 sort of adjectives to describe glycolysis. We're going to say glycolysis is rapid but inefficient. And once we sort of map on some details here, we'll come back and we'll understand how those 2 adjectives really well describe glycolysis. But here's some of those pieces that I said you need to know. I need you to know that glycolysis is 10 reactions, that it occurs in the cytosol, and it is anaerobic. It is able to occur without oxygen, so there's no oxygen required. But let's come back here just for a second. Remember when we were looking at this slide and we said this represents the exterior cell wall, this represents the lipid bilayer of the mitochondria, right? Both of these are lipid bilayers. You'll notice here that this occurs in the cytosol. All of the rest of our numbers, whether it's pyruvate dehydrogenase, the citric acid cycle, electron transport, oxidative phosphorylation, those all occur in the mitochondria. So this is the only process right now that we're going to study that is a cytosolic process. One of the hallmarks that we'll talk about is whether you are aerobic or anaerobic. In an oversimplified way now will indicate whether or not you can do things in the mitochondria or not. Okay, so the other thing that we want to talk about is we're going to split glycolysis into 2 halves, okay? It actually happens to be 5 reactions and 5 reactions, but this purple part represents what we're going to refer to as our energy investment phase. So again, we're going to talk about energy in it requires us to add in 2 ATP to do this process. So again, this is going to be energy investment. Okay, so what's going to happen here, we're going to also refer to this as stage 1. I want you to be able to describe in words what's happening in stage 1. What happens in stage 1 is we are going to be decorating glucose with phosphates. So we're going to decorate glucose with phosphate. And from now on, I'm just going to be abbreviating phosphate as a P with a circle just to sort of keep things simple. So we're going to decorate glucose with phosphate. Okay, we get that phosphate from ATP, so that's why this is an energy investment phase. Okay, green part here represents our energy recovery phase. So again, this is money or energy out. We are going to get 4 ATP out. So we're going to call this the energy recovery phase. Okay, we're going to refer to this as stage 2. And here's what happens in stage 2. If you are a phosphorylated molecule that is worth more than the magic number of 30.5 kilojoules per mole, you can be used to make ATP. That process is called substrate level phosphorylation. Basically, if you have a phosphate on you, what you can do is you can give it up to ADP, make ATP, but that can only happen if you as a phosphorylated molecule have a value of more than 30.5 kilojoules per mole. So let's write this down. Stage 2 basically is going to be that any molecule, so a molecule that is worth more than 30.5 kilojoules per mole, so any molecule worth more than that magic number of 30.5 kilojoules per mole, okay, that is the value of ATP, okay, it's going to give up its phosphate. And here's again what happens. It's going to give it up to ADP, and it's going to make ATP. This is called substrate level phosphorylation, which from now on, I'm just going to abbreviate SLP with a circle. That is again substrate level phosphorylation. Now, what's really neat about substrate level phosphorylation is it makes ATP quickly, okay? So when we talk about sort of this rapid piece here, the rapid piece for understanding glycolysis has to do with substrate level phosphorylation being a very quick process. If your ATP levels fall, you can quickly make more ATP by taking any molecule that's phosphorylated and worth more than 30.5 kilojoules per mole. You can get it to swap its phosphate, give it to ADP, and you can quickly regenerate ATP in your body. So substrate level phosphorylation is a very rapid way to make energy. So let's get to this inefficient piece here, okay? The inefficiency comes from the fact that, going back to our sponge analogy, if we start with a sponge that we cut in half, make 2 smaller sponges, 2 3-carbon sponges, but we really haven't squeezed much of the water out of them, we still have fuel that's valuable. And that's really what pyruvate is. So remember, pyruvate is the end product of glycolysis. But really what we have in this sponge, if you will, is we've got lots of energy left over. So lots of energy left over. And that's why we say that glycolysis is inefficient. You sort of left a lot of fuel on the table, if you will. You did a quick process to make ATP, but then you still have a lot of energy left over. Again, a sponge that we cut in half and just squeezed a little bit. So glycolysis is a rapid but inefficient process. A couple of other things that I just sort of want to map on here. We talked about this already. But when you reverse glycolysis, that is gluconeogenesis. And when we learn about gluconeogenesis next year, we'll talk about the fact that, well, it's not an exact reversal. 8 out of the 10 steps you can directly reverse. But 2 steps, we have to find another pathway. And therein is part of the challenges of how we do gluconeogenesis. So we'll learn about that next semester when we talk about glycolysis. The last little thing to tie in here, and let me actually put on here, I want to sort of map on where we make ATP. So again, here is a place that we make ATP. You don't need to know these details, but I just want to highlight that there's a molecule that's worth more than 30.5 kilojoules per mole. Here's a molecule that's worth more than 30.5 kilojoules per mole. So these are the two substrate level phosphorylation steps. Okay, you don't need to know that for now, but I just wanted to tie in and sort of show you these pieces. Okay, one of the other pieces that's important, and I'm going to highlight it here, is this production of NADH. Okay, so this happens here, that production of NADH. Now, why that's important, it's an alternative currency. It's still money. We're going to cash it in the electron transport chain. But here is part of the problem. If you want this rapid but inefficient process to continue, two things have to happen. You have to make sure that you have a renewed source of NAD+, and you have to make sure that you don't accumulate pyruvate, because the accumulation of pyruvate is going to feed back and inhibit this process. So let's see, let's do this in yellow here. Okay, so if you want to continue glycolysis, here's two things that are important. Okay, so if you want to continue glycolysis, you have to have more NAD+, because that's a substrate for this process. That's a cofactor that's necessary to keep going through this process. You have to have more NAD+, and you have to eliminate, let's actually even say this, we have to have less pyruvate. So you have to make sure you regenerate your NAD+ so you can keep going, and you have to make sure that you don't allow pyruvate to accumulate, because the accumulation of pyruvate is going to feed back and inhibit this process. Those two pieces, they might not seem like they're an important sort of obvious piece to this story, but they really are, okay? Because when we learn some of these other processes, we're going to address how we regenerate NAD+ and how we manage the accumulation of pyruvate and eliminate it to allow a process like glycolysis to continue. And that's our 30,000 foot flyover of glycolysis.